Okay, today we are going to talk about Einstein's own resolution to the twin paradox. But first, a quick primer on relativity. Relativity actually began in the 1630s. Galileo made some observations about motion and drew some very interesting conclusions, and it helped answer the age-old question, what happens when I throw a tennis ball straight up while riding in a moving car? Although Galileo didn't have a tennis ball or a moving car back then, but he did ponder questions like these, and he said the following: shut yourself up with some friends in the main cabin below decks of some large ship, and have with you some flies, butterflies, and other small flying animals. Hang up a bottle that empties drop by drop into a vessel beneath it. With the ship standing still, observe carefully how the little animals fly with equal speed to all sides of the cabin. The drops fall into the vessel beneath, and in throwing something to your friends, you need to throw it no more strongly in one direction than another, the distances being equal. Then, when you have observed all of these things carefully, have the ship proceed with any speed you like so long as the motion is uniform and not fluctuating this way and that. Meaning that the ship is no longer accelerating or decelerating or changing direction, it's just cruising speed, constant velocity. You will discover not the least change in all of the effects named, nor could you tell from any of them whether the ship was moving or standing still. So this was kind of the birth of the concept of relative motion, where you wouldn't be able to assume that something is moving or stationary in an absolute sense, because you wouldn't be able to conduct any experiment to prove it one way or the other. All you could do is just show that at some point later you either are in motion relative to something else or stationary relative to something else. By the way, how understanding were Galileo's friends, right? I know I couldn't pull that off. Hey, what are you doing this weekend? You want to go out on the boat? I know the weather's going to be nice, but we're going to be below deck the entire time. I'm going to bring some flies and butterflies and do you have that bottle of wine? Bring the bottle of wine. No, we're not going to drink it. We're just going to poke a hole in the cork and watch it drip onto the floor. Oh, you have plans. So, okay. So, that's kind of what would happen there. So kudos to Galileo's friends for hanging in there with him. So anyway, once the sailing ship reaches constant velocity, it becomes its own floating inertial reference frame. Galileo realized that with no view to the outside world, there is no experiment you could conduct to determine whether you are moving or not. So if you're on a boat where you can't see the outside world, or you're riding down the highway in a camper with the shades pulled down, and you're conducting all kinds of experiments, whether you're throwing a tennis ball straight up or not, everybody is moving as a moving frame, but within that frame they're all traveling at the same velocity, and in that tiny little world there, everything appears to be the same as if you were stationary, and you wouldn't be able to conduct an experiment to prove that. The laws of physics on the moving ship are the same as they are for the stationary one, again, provided that the ship is not accelerating. So we're going to skip over a bunch of stuff. Obviously a lot of stuff happened, but we're going to jump straight to Einstein 1905. Einstein was a fan of Galileo's work, and he felt that relativity needed an upgrade, because relativity focused on the laws of motion up to that point, and Einstein had familiarized himself with electrodynamics, generation and propagation of light. And so Einstein wanted to incorporate light into relativity, which I guess we could look at as relativity 2.0. So he inserted a few postulates in this famous 1900 paper. The first would basically be talking about Galileo's principle. Galileo's principle is to be preserved. No reference frame will be considered an absolute rest frame. That is, all motion at constant velocity is to be considered relative, and the laws of physics for moving frames of reference are the same as the laws of physics that apply to stationary frames. So far so good. And then Einstein just brings in the light propagation, the electrodynamics in to say that it would apply, light behavior would not do anything different or give away any clues that you're moving any more than Galileo's basic laws of motion. And he says, and I'm paraphrasing with these statements here, but the velocity of light is to be considered constant regardless of the state of motion of the light source. And he also concluded that the existence of an ether was not necessary for this theory as well. So Einstein knew that observing the propagation of light from two different observers in two different situations, the propagation of light would be a single event yet for one of the observers the distance traveled would be different than the other observer, but yet the speed would have to come out to be the same. So mathematically, simple math here, time would tick at a different rate for one person than another, so that the speed could come out to be the same. So the distance is different, the time is different, but then it all equals the same light speed. And Einstein says if there are two stationary clocks at point A and point B, and the clocks are synchronized, and the clock at point A moves to the clock at point B with velocity v, upon its arrival at point B, the clocks will no longer be in sync. The clock in motion A will be lagging behind the stationary clock B. Again from his 1905 paper. So where trouble started was where we would take two of the statements out of the 1905 paper and actually look at them side by side to see if they contradict one another. Because on the one hand, upholding Galileo's principle, and everybody's kind of on an equal footing. Nobody's considered absolute motion, nobody's considered absolute rest. It's just relative. Either you're in relative motion compared to someone else, or you are both considered stationary, but it's all relative and nobody has any preferred frame over the other. However, having said that, then how could Einstein go on to say later in that same paper that clock A was the one that would lag behind clock B and not both? So if we saw clock A in motion, and from the perspective of clock B, he would see clock A in motion, wouldn't A see clock B in motion and consider himself to be standing still? So this is where trouble started with the 1905 paper and the birth of the twin paradox. Essentially, if all motion is relative, then how do we explain why clock A ran slower than clock B and not the other way around? Why was clock A in that preferred frame? I'm going to skip ahead here to 1924, but as you see, we'll go back to 1918 for Einstein's actual introduction of the explanation for how this could possibly be. But in 1924, physicist Max Born said the clock paradox is due to a false application of the special theory of relativity, namely to a case where the methods of general relativity should be applied. So what the heck does that mean? Well, we're not going to study general relativity in its entirety. Thankfully, we don't need to. We're just going to extract a tiny little part called the equivalence principle and talk about the elevator, the famous elevator experiment. Einstein, and this was, to me, this was one of the most genius moments in Einstein's career. But he actually determined that if you were in outer space outside of a gravitational field, if you are in an accelerating frame, that would completely mimic being in a gravitational field and not moving. So if I'm in an elevator car on the ground floor, but I haven't pressed any buttons and the elevator hasn't started moving, I'm in gravity. I'm on planet Earth on the surface. So if I take out a tennis ball and let go of it, it's going to fall to the floor. And Einstein observed that if that same elevator car were actually being pulled by a cable by a rocket ship out in outer space where there was no gravity, but yet the rocket ship was constantly accelerating at a rate to mimic or match what you would feel on Earth, then the floor of the elevator would constantly be pushing on your feet because it's in a constant state of acceleration, and you would feel that. And if you took a tennis ball out, you would let go of the tennis ball. In this particular case, the tennis ball would stay right where it was and the floor would come up to meet the tennis ball, but you wouldn't know the difference between the two because everything would appear to be the same. So that is the famous elevator experiment from the principle of equivalence that was formally written about by Einstein in 1911. The thoughts by Einstein started on that in 1907, but his comprehensive work on that began in 1911. So what Einstein also observed is how light signals would behave in various parts of that elevator car, as it were, either in outer space or on planet Earth. And what he saw would be a frequency shift, where if you're familiar with red shifting or blue shifting, that's great. If not, I can use the pulse method that Richard Feynman used in his explanation, where instead of light of a certain color being generated from the ceiling or the floor, we could say that the light is coming out in strobe bursts, maybe 1 per second. And so if we were on the floor of the elevator and we're watching light pulses coming from the ceiling of the elevator as the elevator were accelerating in outer space, then the floor of the elevator would be constantly accelerating to meet those light signals. And even though from the source, from the origin, they were pulsed at exactly 1 second apart, we're coming up to meet the light signals, so we're seeing them in shorter intervals than 1 second between the pulses. And we would see that if we were to look at those intervals as an actual clock, a timekeeping device, then we would conclude that the clocks on the ceiling of the elevator would be running faster than on the floor where we would be. If we actually transported ourselves to the ceiling of the elevator and watched light signals being generated from the floor, the opposite effect would happen. We would actually be in a constant state of acceleration away from those light signals, and they would take extra time to have to catch up to us while we're accelerating away, and the intervals between the pulses would actually take more than 1 second. So we would view that as the clock on the floor as running slower than ours. So in essence, if you're on the ceiling, your clock is running faster. If you're on the floor of the elevator, your clock is running slower. The two things that contribute to this are the faster the rate of acceleration, the more pronounced the difference is going to be between the rate that your clocks run. So that makes sense. The faster you accelerate, then you're either meeting those signals more quickly or traveling away from them more quickly to create a bigger difference. And the other thing would be the height of the elevator matters too, because if it's an elevator that's an 8-foot ceiling versus an elevator that's a 12-foot ceiling, with a 12-foot ceiling, you now have more space for the signals to either stretch or compress from the floor to the ceiling. So at any given rate of acceleration, given more space for it to do its thing, stretch or compress, you're going to get a more pronounced effect. So those two things together would conclude what the difference is in the clock rates. Okay. Now Einstein said that, well, since gravity and acceleration are equal, and we've just proven that in a state of acceleration in outer space, the clocks would run differently, then in gravity those clocks would run differently as well, even though on planet Earth you're not moving, but you're feeling gravity. And that actually has been experimentally verified, so very impressive. So for A times h, A would be the acceleration value and h would be the height. Those two contributing factors would decide how differently those clocks would run. Einstein just combined the A and the h into one mathematical term and called it the gravitational potential for that accelerating system. And assume that the relation which we have deduced for the homogeneous gravitational field also holds for other forms of field. So basically, anything like a real gravitational field or anything in a state of any type of acceleration which would mimic a gravitational field, Einstein is saying that we've got a gravitational potential there, and what we had just described in terms of the light signals and everything else would also be applicable for those examples as well. Okay. So why are we getting into all this? Again, Max Born said that we need some general relativity to explain the twin paradox. So now that we know acceleration is the same as gravity, and either or, according to Einstein, will create differences in how clocks run depending on where you are, either in that state of acceleration or the gravitational field. Now we're going to put this back into the twin paradox, which again, the twin paradox is you've got two twins on Earth, one gets in a rocket ship, travels at a high speed, turns around, comes back and finds that his brother has aged quite a bit. So he missed a lot of birthdays. So acceleration will produce a simulated gravitational field at the turnaround point. So remember, when the traveling twin slams on the brakes and turns around and reaccelerates toward Earth, then that person in that ship is feeling gravity, is in a simulated gravitational field, and according to Einstein, while that person is feeling that gravity, that person's clock will run differently because of all the conclusions that he had made earlier. Okay, so Albert with clock A, Max Born having clock B, Albert in the traveling ship at that point of turnaround, he will see clock B running much faster during this time to compensate for the reciprocal slowing effect seen during steps 1 and 3. As a result, Max Born will be much older than Albert by the time he gets back to Earth. So I'm going to explain what steps 1 and steps 3 are, actually. Because this solves the paradox while preserving Galileo's principle during inertial motion. So Remember the little jam that Einstein got himself into by saying that Galileo's principle will hold, there won't be any preferred frame of reference, and anything considered to be in motion, it would be in motion relative just to something else, and there's no absolute nature about that. And then they said, well, wait a minute, what about why is A slower and why is B not? So what Einstein clarified about his own theory in 1918 was during the constant velocity portion, or the inertial portion of the journey, which would be most of the journey, and that would be steps 1, where the ship is traveling at a constant velocity away from the twin brother on Earth, but then slams on the brakes and experiences acceleration during that turnaround, and then once he re-achieves that desired velocity, then it will go at cruising speed at that high velocity in step 3 all the way back to Earth. So step 2 is where the acceleration occurs, and that's where the gravity is felt, and that's where Einstein's clock will be running so much slower that he will see Max Born's clock running so much faster than his. But during steps 1 and 3, they will actually each view the other's clock as running slower at the same time. So that's a mind-blowing concept, but that's what Einstein proposed has happened. So what that does is that preserves Galileo's principle. Einstein will see clock B running slower than himself, even though Einstein considers himself in motion, but Max Born will see Einstein's clock running slower than himself as well, even though Max Born is still on Earth because of the relative nature of the theory. With each of them seeing the other clock running slower at the same time, you might think, well, how could that possibly happen? And what undoes the paradox is that crucial step where only Einstein is in the gravitational field at the point where that gravitational field is created. So he's in that lower clock position, and Max Born's clock runs faster during that crucial, and that more than compensates for the fact that their clocks are each running slower from each's perspective in steps 1 and 3. So that takes care of Galileo's principle and Einstein's explanation for why, in the end, clock A still will have run slower than clock B, and it's that crucial acceleration part that undoes and by the way, the steps 1 and 3, where that crazy thing happens to both of them at the same time, that is typically called reciprocal time dilation or symmetrical time dilation, because each is observing the same thing, a slowing effect. It's really tough to take, because usually things happen in opposites. If I'm taller than you are shorter than me. If I run faster than you, then that means you are running slower than I am. So by comparison, things tend to, when there's a difference between two things, you can make a statement about from one perspective, and then the opposite would be true from the other perspective. But in this case, at steps 1 and 3, both clocks are running slow from the perspective of the other at the same time. Okay? But wait, won't Max Born see a blue shifting of signals from Albert's clock too? Yes, that effect will occur after Einstein sees Max's signal blue shifting, but they will be by the same amount and for the same length of time. So here's where trouble sets in on the 1918 resolution to the paradox, because when the elevator model was first introduced and compared to gravity, those two models were different than what's happening here at the turnaround point for the twin paradox. Okay, because remember, in the elevator, the faster clock was the higher clock, and this lower clock was the lower clock. And Einstein concluded that since gravity and acceleration are equal, clocks in a gravitational field experience the same time dilation effects as clocks in an accelerating frame of reference. But mechanistically, this effect is actually produced by the fact that the ceiling and the floor maintain the same distance from each other during the entire journey. And so therefore, one will be traveling toward the other's signals, and the other one will be traveling away from the other signals. So you will get the blue shifting and the red shifting at opposite ends, or the stretching of the pulses in terms of time intervals, or the compression. So, but what that hinges on is the fact that the elevator experiment is the distance between those two clocks remains constant, so that state of acceleration can produce that effect. So in the original acceleration model and the gravity model, the extent of the light signal shifting is a condition or co-effect of how much time dilation will be measured for each. And if you read the entirety of Einstein's 1911 paper, that's what you would see. However, in this 1918 setup, which does not resemble either of the previous models, we have blue shifting for each observer instead of blue for one and red for the other. So this is kind of a problem because now you can no longer claim that the light signals, which was what was used to propose the difference in clock rates to begin with, the light signals are no longer synonymous with what you're saying about the clock behavior for the two different clocks. So there we go. And again, this traces back to the 1911 paper. So Einstein proposed the time slowing effect during acceleration through careful analysis of the light signals. And he equated the effect to what would happen in gravity, but then he deemed the same thing to occur in all forms of simulated gravity and applied that to 1918 twin paradox resolution, even though that didn't produce the same light signal effects that allowed him to conclude how clock rates change in gravity and acceleration to begin with. So I first wrote about this, I think, in 2007, and then again in 2008. But sadly, I will not be getting the Nobel Prize for this because after a long journey of digging deep, I actually finally found a reference in a very small textbook in a community college library years later that was written in 1967. So this guy beat me to it because if you look at this statement, he's pretty much saying the same thing. For instance, one might expect that the variation of the Doppler effect during the reversal, the turnaround period, would also affect B's reading of A's clock, since this effect is a reciprocal phenomenon depending only on the relative velocity. No reason is given for ignoring this aspect of the principle of equivalence. In other words, this guy's saying exactly what I said. We're getting blue shifting for both. Not at exactly the same time, but that's really of no consequence. Because we're not getting blue for one and red for the other, which would have defined the one clock running faster and the other clock running slower. So this gentleman back in 1967 saw this as a problem as well. Okay, so the simulated gravity is isolated to location of acceleration. The extent of the blue shifting depends only on the acceleration value, and in this case, not the distance. Now remember, the distance in the elevator box was a contributing factor because the distance didn't change between the floor and the ceiling. In this case, you've got a constant distance change, and that's actually what's creating the shift in the signals from the acceleration here. So the distance between Born and Einstein is actually shrinking as the pseudo-gravity effect is being created. And what I propose is the extent of the blue shifting wouldn't matter when Einstein decided to turn around. Einstein could have turned around at the halfway point instead, but if he turned around and reaccelerated with the same acceleration value, it would create the same blue shifting signals for the same amount of time until he achieved that velocity. Or if he traveled longer, he would get the same blue shifting effect for that as well. Okay, so the extent of the blue shifting and for how long would only be dictated by what's happening during the acceleration phase, and wouldn't be dictated by how far out the individual has traveled. So you must be thinking that's going to give me the Nobel Prize. Now remember, the greater the distance between the clocks, the more the clock rates will differ. Again, on the elevator example, because those distances remain fixed between the ceiling and the floor throughout, and that's what actually creates that equal and opposite effect. But the longer distance you have between the two, the more opportunity you have for those signals to expand or compress. And both are going to happen in an opposite fashion from each other's perspective. Okay, so that only works in the 1911 model and not in the 1918 model. But no Nobel Prize for me. And I had actually read this paper a long time ago, 2007 maybe. And as I was preparing for this, I pulled out a bunch of old papers and dusted off that I hadn't seen in quite a while. And as I was reading through this, I saw that this person had an issue with this, and pretty much is saying the same thing. What he's doing, I'm making an issue about the Einstein being the single traveler and deciding to vary his turnaround points and therefore changing the distance h. In this case, this person's just saying the same thing. They're just saying that, well, let's say we have multiple clocks at different distances and clock B decides to turn around, then if all of those clocks are synced with respect to each other, which is another whole thing, but let's assume that they are, then how could G possibly get all these different values between itself and clock A, clock C, and clock D, because they were all at different fixed positions, and their H values would be different for all of them. So, so this person saw that as a problem too. So, anyway, so there is some inconsistency and just flat out logical dismissal of this explanation, for two reasons. Because of the light signals no longer behave in the way that Einstein was able to prove the clock differences to begin with, and the variation of the H value is of no consequence when comparing the extent of the blue shifting as well. So, so that's a real problem. So that kind of eliminates the general theory of relativity explanation as a viable way to explain the conundrum that began in 1905. Now, let's look at steps 1 and steps 3, which would be that crazy assumption that my clock is running slower than yours, while at the same time yours is running slower than mine at the same time. Is that possible? Is reciprocal or symmetrical time dilation during steps 1 and 3, the relative inertial motion, is that even possible? Well, if we look at a little bit of the science of GPS satellites and how they relate to relativity, one good thing about GPS satellites and relativity is they actually are further verification that time dilation actually is a real physical phenomenon, and it exists for both scenarios that were proposed, both with changing gravitational positions. Atomic clocks will run either faster or slower, and in changing velocities, atomic clocks will run slower. But what we're looking at is, will the two clocks at the same time each see each other's clocks running slower than their own simultaneously for that reciprocal effect? Okay, so the GPS system has orbiting satellites, has ground control atomic clocks, and it has those receivers all over the place that you either buy and plug into your cigarette lighter, or smartphones have the same thing so that you can do a navigation. So basically all those three components are clocks, so to speak, or reading clocks, and they all need to be synced up and function very accurately so that you know exactly where you are when you're getting a good signal for those. So the GPS system as a whole needs to operate in sync. All the moving parts of the system are in various gravitational positions and are also in relative motion. In order to function, the clocks are pre-adjusted to run at artificial rates to compensate for rate changes. So in other words, I could sync two clocks that are actually running differently for relativistic reasons. So if I have a clock that's at the top of a building and it's a very sensitive atomic clock, and I find out that it's enough to throw off that atomic clock and it actually runs at a faster rate than my clock way down here on the surface of the Earth, then I could recognize that it's because time elapses differently in those two gravitational positions, but I could artificially either speed up one of the clocks or slow down one of the clocks so that they're artificially ticking off at exactly the same rate. So when we're talking about syncing GPS clocks in different locations, like on the satellites or on the ground control stations, we're recognizing the fact that time is actually elapsing differently, but the clocks themselves are artificially either sped up or slowed down so that they can actually tick in unison. Okay, so that's what happens in the GPS system. Okay, the question is does that in fact prove the entirety of Einstein's relativity, or does it actually disprove a component of Einstein's relativity? Well, let's take a look. If we have two clocks that are being compared, and these two clocks are in relative motion, Maybe the yellow one is on Earth and the white one is traveling on a spaceship overhead with some sort of constant velocity, then according to Einstein, from the position of Earth, I would see that white clock running slower than mine for relativistic for reasons. But according to Einstein, that white clock, as it is whizzing by, would see the yellow clock on Earth running slower than itself. Okay? So if the yellow clock artificially slows its rate just enough, then it can run in sync with the white clock. Because again, I'm the yellow clock and I see the white clock running slower, but I want the clocks to be ticking in unison, in sync. But I see that this white clock is running slower than mine. So I actually artificially, mechanically slow down my yellow clock so that it now ticks in unison with this white clock that I see flying overhead. Okay? But we have a problem. The white clock already saw the yellow clock running slower, according to Einstein, from its own perspective. And now that I have artificially slowed the yellow clock, the white clock already saw the yellow clock running slower. Now the white clock will see the yellow clock running slower and further out of sync, farther out of unison. Okay? So the moral of the story is, if Einstein's relativity is correct and you have that reciprocal time dilation, then it would be impossible to two-way sync clocks in relative motion. Because if I adjust one artificially to compensate for the other, then fine, I can now claim that I'm ticking in unison with this guy up traveling at a velocity, but now that clock will then see my clock running even further out of whack. So making an adjustment on one end throws it farther out of sync from the other end. So logically, there's no way that you can do the two. Okay, so the GPS clocks are in constant relative motion with the ground clocks. And again, this is something that I came up with, I think, in 2007 and wrote about it and eventually put it on the FQXI essay contest site. And so something I just kind of hammered out and used as a way to analyze that version of Einstein's relativity. And again, Nobel Prize, right? No. Years later, I think this was 2014, I was perusing a couple of blog sites, and on one particular physics blog, I saw some folks conversing about this particular book that was talking about GPS. And so I'm reading, but previous to that, I couldn't find anybody that came up with these conclusions that I did. And so I saw the name of the book, the name of the author, or ordered, actually there were two copies of the books. There was one that was a second edition and a first edition. The first edition was actually from 2006. So I ordered both copies and read word for word the gentleman's section on GPS and relativity. And he said this: despite the relative motion, Earth clock, does not run slow, nor look like it is running slow to any of the moving satellites, nor is it measured by them as running slow. Hence, it is in direct disagreement with fact to assert reciprocity, or the reciprocal or symmetrical time dilation, as special relativity does, such that symmetry prevails between the Earth clock and the satellite clock. In reality, there is an objectively real asymmetry, otherwise the compensation would not work, meaning that you have to have that asymmetry in order to be able to sync the clocks from both directions and have the entire system running in sync. And that was Thomas Phipps Jr. from Old Physics for New, and those statements are actually in his first 2006 edition, which predates me. Now, I actually welcome more simple experiments, because I've been dialoguing with folks for years on this, and it's a little tough for people to take. Number one, just because you're stating something about Einstein's theory that's you're saying is not correct. So that in itself, kind of gets people's emotions up, even though they're PhD scientists. But anyhow. But the other thing is it is, I will admit, it is a complicated GPS. It is a complicated experiment, because you're dealing with gravity, you're dealing with relative relative velocity, and you're dealing with rotational motion, which has effects that need to be considered all at the same time. And so, you know, someone could just say, well, that doesn't apply, and it does apply. You have, in addition to gravity, which would just be considered a clock adjustment, you absolutely have relative motion between the ground clocks and the satellite clocks. First of all, the clocks are all moving in different planes, so to speak, and well, anyway, so it's complicated, but it works. I would actually welcome an extremely simple experiment to test this, which would make it a little bit more palatable for folks to consider this reciprocal time dilation and whether it really holds up in physical experiment. A variation of the original Ives Stilwell experiment would be great, because that would be linear. The Ives Stilwell experiment actually used a moving source, and it looked at the Doppler shifting, the relativistic Doppler shifting of light signals from that moving source. So somebody did a variation of that, and the source was on Earth considered to be not moving, and the measuring device was the thing that was moving, and you still got a relativistic Doppler shift from a linear experiment that ran opposite of what Ives Stilwell did. Then hey, somebody should do that. That would be great. You might argue that out of the 1960s there was a bunch of different rotating frame experiments, tabletop experiments basically, where Doppler shifts were measured from either a source at the center and a absorber or a measuring device at the edge of the rotating frame, and then vice versa. But a couple problems with that is that it actually wouldn't prove, because you actually do get opposite effects there. You actually get a blue shifting from one direction and a red shifting from the other. In addition, I guess the most well-respected experiment coming out of that era was the one run by Kundig, but later it was determined that the analysis of the raw data from the Kundig experiment was up to 20% off from the actual conclusion that he drew from there. So that was kind of a mess. And by the way, the relativity of the rotating frame in itself would be different than the GPS experiment, for those of you who are wondering, because you've got either a source or an absorber at dead center, and you're basically looking at a rotation in a single frame. Comparing that to GPS is entirely different, because you have the rotation of the Earth in one plane, you have the GPS clocks on the surface of the Earth, which are about, I don't know, like 25% out from the center, and then meanwhile you have the satellite clocks, which are rotating in an entirely different frame. So in 3 dimensions, you've got all kinds of distance changes, constant distance changes between the surface clocks and the satellite clocks, where with a tabletop experiment and a strictly rotating frame, you do not have any distance changes between the two clocks, so to speak. So I would welcome that. So in short, the Einstein proposal from 1918 does not hold up or bail out his original conundrum that he created in 1905, but thankfully there have been experiments that have come along that have actually proven the concept of time dilation, which is a very important consequence of relativity. So you win a few, you lose a few. So feel free to comment.